Today's goal is to solve quadratic inequalities. Solve, of course, means find the solutions, the values that make a true statement. Quadratic means it'll have the form x squared, ax squared plus bx plus c. And inequalities means not equal to. So these would be symbols like less than or equal to, greater than or equal to, or simply does not equal. So take a look at our first example. We're asked to solve or find which x values will make this true. We can see it's quadratic because it's in the form x squared plus bx plus c, and it's not equal. X squared minus x should be greater than 6. So we're going to solve this in two different ways. The first way I want you to think about this is we're going to think about this graphically. In order to think about it graphically, we're going to find an analogous function. And it's easiest to find the roots of the function. It's a little hard to compare to 6. So we'll get one side equal to 0, and then we'll say, okay, what is the analogous function? It would be f of x is equal to x squared minus x minus 6. Okay, well, what do we know about that function and how it compares to 0? Well, if we want to set it equal to 0, then we can find some roots. So we've got 0 is equal to x squared minus x minus 6. We're taking a little detour here. You'll see why very soon. So this function f of x has roots at x equals 3 and negative 2. Well, then we know what the function looks like. It looks like this. We know it's concave up because it has the unwritten leading coefficient of positive 1. And so if it has roots at negative 2 and 3, if we go back to the original inequality, this guy, or similarly, this is the exact same inequality, it's just written in a different form, we're asking ourselves, where is the function positive? Where does it have y values that are bigger than 0? Well, it has y values bigger than 0 if you go left of the x value negative 2 or right of the x value 3. So what this inequality is asking us is which x values can you substitute into this function that will produce y values that are positive? Well, the x values you can substitute in are those to the left of negative 2 and also those to the right of 3. Let's just double check our answers and make sure this makes sense. Okay, let's give ourselves a quick check. What we're saying is that, for example, negative 2 will not make this inequality true. Let's go back to the original inequality. If we substitute negative 2 in, we square it, we subtract it, it shouldn't be greater than 6. That's why we're using parentheses here in our answer. Well, if we square it, we get 4 plus 2 isn't greater than 6. Well, that's true. 6 is equal to 6. It's not strictly greater than 6. But values to the left of negative 2 should work. Try it. Substitute in negative 10. Similarly, anything to the right of, but not including 3 should work. So, for example, 5 should work. If we square 5 and subtract 5, we should get something this time greater than 6. 25 minus 6 is indeed greater than 6. So these are the x values you can substitute into the analogous function that will produce y values that are positive or above the x-axis. Now, we solved this function graphically. You can also solve it algebraically. Our work is going to start in the same way. Let's copy down the problem again. X squared minus x is greater than 6. We're going to start in the same way, which is to say we're going to get one side of the inequality equal to 0. So we have x squared minus x minus 6 is greater than 0. Again, we're going to find out where is it. We're going to take like a little detour. Where is x squared minus x minus 6 equal to 0? We're going to factor. So far, our work looks identical to the work we did above, and here's where it's going to differ. We're going to make a sign chart, which is a strategy you'll see often in calculus. It may feel a little bit cumbersome today, but it's a strategy you'll see many, many, many times. So on this sign chart, we're going to put what are the values that make our equation equal to 0, because these are our changing points. So for example, the factor x minus 3, it becomes positive for x values bigger than 3. That's like if you substitute in 5. 5 minus 3 is 2. It's a positive number. But it'll be negative everywhere else. For example, if you substitute in the number 0, 0 minus 3 is negative. Or negative 10. I'm just picking any number less than negative 2. Negative 10 minus 3 is also negative. But for the factor x plus 2, it became 0 at negative 2. So it should be positive to the right check it. 0 plus 2, yep, positive. 5 plus 2, positive, yep. And it should have changed signs at -2. So it's negative if you substitute in a value less than -2. And now maybe all this feels a little bit tedious, but here's the beauty. If we know that x minus 3 is negative and x plus 2 is negative, then their product is positive, because a negative times a negative is positive. Likewise, a negative times a positive is negative, and a positive times a positive is positive. And so if we're wanting the values that are greater than 6, or analogously, x squared minus x minus 6 is greater than 0, we don't want to be exactly equal to 0. We want places where my product, x minus 3 times x plus 2, is positive. And so, indeed, we come up with the exact same answer. The product, x minus 3 times x plus 2, will be positive where x is less than -2 or greater than positive 3. Let's take a look at one more example. Let's solve this inequality. Negative x squared is less than or equal to negative 9x. Again, we're going to solve it two different ways just to get a little bit of practice. Okay, we're going to set it equal to 0 on one side. Negative x squared plus 9x is less than or equal to 0. Okay, now I can think about this graphically and say I'm going to call this guy my function, f of x. If I want to see where the function is less than or equal to 0, let's start by finding out where the function is equal to 0. Well, this is nice. We can just factor out a negative x. We're left with x minus 9. So my function has roots at 0 and positive 9. I know that it's going to be concave down because my leading coefficient is a -1. So where is my function less than or equal to 0? Well, it's equal to 0 at 0 and at 9. And the function is less than 0 to the left of 0 and to the right of 9. So the x value is -infinity to 0. This time we're including 0 because we're allowed to be less than or equal to 0. Union 9 to infinity. These are the x values that make our analogous function f of x less than or equal to 0 or negative. Likewise, we could solve this algebraically in the same way. We're going to start by getting the inequality equal to 0. We're going to factor to find out where the places where the inequality is 0. The only difference is that instead of setting up a function, we'll set up a sign chart. This time we're going to mark down 0 and 9 because those are my two x values that make the product equal to 0. Negative x, be careful here. Negative x is going to be negative for values bigger than 0. For example, if you put in 1, -1 is negative, or 10, -10 is negative. And so if you put in a negative number, the opposite of -5 is positive. And for my factor x minus 9, it'll change signs at 9. Just double check. 10 minus 9 is positive. Yep. Anything less than 9, if you subtract 9 from it, will be negative. And so now I want this product, negative x times x minus 9. Cool. This is easy. A positive times a negative is negative. Negative times a negative is positive. Negative times a positive is negative. Now I want my inequality to be less than or equal to 0. So I'm looking for places where my product is negative or equal to 0. So whether you use the sign chart or you draw a quick sketch, either way you should come up with the same answer.